going to talk about one-to-one functions. It's exciting. And without even me telling you what a one-to-one function is, I'm going to ask you about them and see if you can figure out the definition all by yourself. So here's a picture. Two different functions, f and g. Both functions have the same domain. Can someone tell me what the domain is? What is the domain? 1, 2, 3, 4. Yes. A is the domain. It is the set 1, 2, 3, 4. Do you know about any other elements in the domain? No. That's the domain for both. What about, and we'll label this, B1 and B2. What are the ranges? Well, they're B1 and B2. Can someone tell me what B1 is? Yeah. Yeah. Why don't I write that as like 7, 4, 2, 10? Yeah. You can write it that way, but in general, what's the common practice? Yeah, lowest, least to greatest. It just helps a little bit. Okay, so you have the same domain and two different ranges. You have different functions. F is a different function than G. I will tell you this, one of these is a one-to-one function and one of them is not. What is your guess? Raise your hand. Someone make a guess as to which one's one-to-one. Slalom. The top one. F is 1, 2, 1. G is not 1, 2, 1. Is anybody, someone different, does anybody want to explain that to me, why they think F is 1-to-1 and G is not? Just take a guess here. Pang, what do you think?
Because every one domain has one domain has
one, not, you don't want to say one domain. One,
input.
what has, no, close. You have, this is inputs, right? So therefore,
oh, so two inputs has, one output has two inputs.
yes, one output has two inputs. That's correct. Now, the word here, we need a better word than has, right? What we're going to, I've said it before, but I want to make it very clear. You can think of those red arrows as the word maps. 4 maps to 10. The function f maps 3 to 7. The function f maps 2 to 4, maps 1 to 2. In this case, the problem we're running into is two inputs map to the same output. And this is something that's important here, two different. So what does that mean? That means that x1 does not equal x2, but f of x1 what? Equals f of x2. Numerically, what does this mean? 3 does not equal 2, but what? Yes. So let's go back and, so we figured out what one-to-one isn't. We know what one-to-one isn't, but what is one-to-one? So if this is true, if this is what it means for something not to be one-to-one, can someone come up with the definition of what it means for something to be one-to-one? Yeah.
Would it be x1 does not equal x2 and f of x1 does not?
Exactly. And I'm going to put in a few little cleanup here, and then I'll have it in the typed version. If x of x1 does not equal x2, then f of x1 does not equal f of x2. If you have two non-unique, if you have two different x values, the y values have to be different. Numerically, if we write that out here, let me give it to you right here. A function is called one-to-one with this definition right here. A function f is called a one-to-one function if it never takes on the same value twice. That is, f of x1 does not equal f of x2 whenever x1 does not equal x2. What does that mean visually? This function right here, if you graph this function right here, 2 and 3 both map to 4, right? So when you're at 2 and 3, they both map to 4. And what were the other 2 points? We had 1 to 2. And what was the other one? 4 to what? 10. So there's the function right there. What could happen in between all those points? What could happen? If you had to connect those dots, what could you do between the points? Straight line, sine wave, anything you want. But what does this mean right here? We know for certain when you plug in 2, what do you get out? 4. And when you plug in 3, what do you get out? 4. So therefore, 2 different inputs map to the same output. 2 different inputs map to the same output. If you wanted to turn this into a one-to-one function, how many points would you have to move? Yeah, at least 1, right? Let's move this one up here. So we're going to have a horizontal line test. But let's just pause there for 1 second. This function right here, in order for this to not repeat y values, it can't repeat y values. You cannot repeat y values. Meaning, if you had to connect these dots, what are you going to have to do if you can't repeat y values? The function is always going to be? Yes. The function is always going to be? So that's one way to have a one-to-one function. Or, what else could it do? Exactly. Could the function ever stop moving? Could it ever level off? Could the function go up like this and then go up? No, because you would have, here's an x1 value and here's a x2 value, and then you have, let's call that y1 right there. What do we know? We know that f of x1 equals f of x2, but x1 does not equal x2. So therefore, this is not 1 to, it's not 1 to 1. So can it level off? No. The only thing I want to give you notationally, always increasing, I want you to call that always increasing or strictly increasing. I've seen it written as just increasing or decreasing. In some books, some publications, some articles, some teachers will say when they say increasing, what do they actually mean? Strictly increasing. The difference is, in my math background, so I just want to make you familiar with this, this function right here, even if it leveled off, could be called increasing. It is an increasing function. I just want you to be very specific. So when you say a function is one-to-one, you are telling me that it is always increasing or always decreasing. I want you to say what you mean. Some books say this function is increasing. Well, I want you to say it is strictly increasing or strictly decreasing or always or strictly. It's the same thing for me. You okay with that? So if a function if a function is always increasing or decreasing, what is it not doing? Or going back. So just remember this, the function can't level off and it can't level off and it can't change. Yes. So what does it mean by that? So it can't level off, meaning you can't do this, right? Can't level off. And what does it mean by can't change direction with my terrible, terrible handwriting today? It can't change direction. We'll talk about this more when you get back from lunch. Go. We're going to look at this one right here. Here's a table of values. On the x-axis, which we're going to call the t-axis, we have time, 0 through 8, and then we have population at time t. Would you consider, could this be a one-to-one function based on the data that you have available? Is this a one-to-one function based strictly on the data?
Yes.
Yeah. Is there any repetition? Are there any inputs, t-values, that are mapping to the same output? No. Population, by what we can see here, is strictly increasing. That's okay, because you can accelerate in the negative direction. Okay. What about this data set? What changed in table 2? What's the only thing that changed in table 2? Nope. Yeah, the input is now the input. So the input is now the output. So originally we had the population in terms of time. In this case, we have the time in terms of population. So they answer two different questions. This one answers, what is the population at a certain... This one answers, what is the time when the population is at a certain level. could both of these functions be useful in different circumstances? Yeah, you might be able to measure the population really accurately, and you might want to know how long has this been there for. In terms of crime scene forensics, is that a important? Are functions like that used all the time? Yeah, in terms of a crime scene, knowing the time of, let's say it was a murder, the time of death. How do they calculate time of death? How do you calculate time of death if you find let's say someone was clubbed over the head, they die instantly? Well, if they're dead.
If they're dead, they're
Well, like if it's those animals.
Okay, come across a dead person. They're dead, no heartbeat.
Oh, I'm sorry. I'm thinking in terms of before they're actually dead.
No. I'm talking about, okay, they've been dead. How do they calculate? You see that all the time. They calculate. We think that we're pretty accurate. They die between 2 and 2:30, and they're pretty accurate.
Like certain things happen.
What happens after you die? That's a deep question for a math class.
Wow.
Your heart stops beating, your blood stops moving. You get all like stiff.
Yep, you get stiff, so rigor mortis can be a factor, sure. When you get sick, what can happen to your physiology?
Temperature.
Yes, so when you die, what happens?
It's cold, so based on your temperature, you can find out.
Exactly, yeah. You measure the temperature of the body, and that's accurate. I think can be an accurate predictor for the first 20 hours, 24 hours, something like that. Something like
Over
that.
You have to
Do other things. But there are other things too that make it more accurate. But temperature, you have certain cooling. So, that would be a data, an input, which isn't time, but what do you get out of it? Time. You input the temperature, and you know that there's a certain function that dictates how fast the body cools. We could actually look that up. I will look that up in one of our breaks. Okay, so here's the deal, though. You see this new notation up there? You see it up there? What does that mean? Well, we're going to get to that in a second. Here's a nice diagram. Is this a one-to-one function? No. Why? It switches direction, sure. It is not or decreasing. Two x values which are not identical map to the same y value. What kind of line is this? It is straight. Can you be more specific? It is a horizontal line. Exactly. We have a horizontal line test. Here is what it says. A function is called one-to-one if and only if no horizontal line intersects its graph more than once. If a horizontal line intersects more than once, it means that two different x values are mapped to the same y value. Two different x values. So, is it pretty easy to visually come to a conclusion about whether a function is one-to-one or not? Sure. You look at it and you're answering, does it turn around? So it's something like this. Is it one-to-one? Nope. Something like this, one-to-one? Looks like it. Something like that, one-to-one? Yeah, strictly decreasing. So figuring out if something one-to-one visually is pretty straightforward. How many horizontal lines do you need to prove that something is not one-to-one? Just need one. Could you have an infinite number? Could you have 7? Absolutely. You could have as many as you want or as few as you want. But as long as you have just one, it is not one-to-one. What about some examples here? So, without saying it out loud, just think about this in your head. Think about what the graph of x cubed looks like. Think about what the graph of x cubed looks like, and then answer the question in your head, is that one-to-one? Without saying it out loud. What do you think? Is it one-to-one? Who thinks no? It's not one-to-one. Who thinks yes? It is one-to-one. Why do you think it's one-to-one? Visually speaking, what does it look like? It looks like.
Yeah, so that would be a lot.
Is that it?
So I guess technically,
Yeah, I think so.
It's a little tricky. I mean, you're probably focusing your analysis right there, right? What happens at that point? You don't have the math to prove this yet, but at that point, the function is neither increasing or decreasing, but it's only increasing. It's only constant for one point. Everywhere else, this function is. It is always increasing. Yeah, it is always increasing. So therefore, this is 1-to-1. You can also say it this way: if x1 does not equal x2, then x1 squared does not equal Sorry, x2 cubed, x1 cubed does not equal x2 cubed. If you have two different numbers, there's no way to get the same output with two different numbers if you're cubing it. Every number cubed goes to a different number. Every number cubed. What about y equals x squared? Someone raise their hand, I will call on you, and you can tell me. Y equals x squared. Is that 1-to-1? Raise your hand, and I will call on somebody. Yeah, what do you think? No, it's not. You have x squared here. Visually, how many horizontal lines can you draw that pass through more than one point? Many of them, an infinite number. That's great. Anything where y equals greater than 0, right? Anything y equals greater than 0, boom. Y equals b, you have the square root of, negative square root of b there, and what do you have right there? Positive square root of b. What does this mean? When x1 equals the opposite of x1, then x1 squared equals negative x1 squared. So we have two different values. x1 and negative x1 are two different values. Negative root b, positive root b. They both square to b. Is this a one-to-one function? No, it is not. Let f be a one-to-one function with domain A and range b. Then its inverse function, f with that little negative 1 up there, has domain b and range a, and is defined by f inverse of y equals x, if and only if f of x equals y. Let me put some notes in there. This is some new notation. That means if and only if. If and only if. This means f inverse of y equals x, and this means f of x equals y. If you have one set, the input a, here's a, there's a value r, and the function f maps it to a set b, and let's call that value s right there. F takes the value r from a and maps it to the value s in what set? B. It takes things from the domain A and maps it to the range B. What does F inverse do? So F of R is equal to S. What does F inverse do? What do you think? Absolutely. The inverse is the opposite direction. It takes everything that F mapped to B, and what does it do? It undoes it. It undoes the operation. F inverse undoes F. F inverse undoes F. Let's say F brought half of these values over here, but the other function only brought half of them back. Is that the inverse? What do you think? If F inverse only works for half of the values, is it the true inverse? No. It has to map them all. So this function f, it could take r, it could take how many values could be in a? How many values could be in the domain? An infinite number, as many as you want. If there are an infinite number of things being mapped to b, those infinite things, those infinite outputs, all have to be mapped back to the exact same one. So if r goes to s, s has to get mapped back to r. It can't get mapped back to something else. This definition also tells you something really, really key here, and this is probably one of the more powerful things in the entire lesson. It tells you something in here. It says, if f is a function where the domain is a and the range is b, its inverse has domain b and range a. What does that mean? It means the domain of f inverse is the range of f, and the range of f inverse is the domain. Why is this really helpful? We had trouble finding something in the past. I'll give you a hint. Not domain, but you said it. Range. Finding domain pretty straightforward. We avoid dividing by 0, and we avoid taking an even root of a negative number, right? Square root or fourth root of a negative number. Imaginaries, we don't avoid those. Range was more challenging. You had to do a lot more logic. Can someone give me a new way of finding the range of a function? You find the domain of the inverse. You find the domain of the inverse. If you found the domain of the inverse, you have found the range of the function. So now you need to ask yourself, how do I find the inverse? If you have a function, do you guys have a way of finding the domain? But you need a function to start with. So let's do a nice, simple example. Is this a function right here? Absolutely. Starts with x. Let's say 1, 2, 3, 4. Plug in 1. What do you get? 2? 3? 4? So f takes all the x values and maps it to y. What is f inverse going to do? Take all the y values and map it to x. So when you plug 5 into f inverse, what are you going to get out? 4. When you plug in 3, what are you going to get out? When you plug in 1, what are you going to get out? When you plug in -1, what are you going to get out? 1. See if you can find out what that relationship is. Please find for me f inverse. What is f inverse? What is f inverse of x? See if you can figure that out. Work for all functions that I could throw at you. All one-to-one functions I could throw at you. Here is a nice, simple, straightforward process that you get to follow. Right, y equals f of x. So come up with, someone give me a linear function, any linear function. 3x plus 5. Is that one-to-one? Yeah, all linear functions except for constant functions are going to be increasing or decreasing, strictly speaking. So they're all going to be one-to-one. That's good. Solve this equation for x in terms of y and then express it by interchanging x and y. So you can do the interchange first. I like doing the interchange first. So step 1, you can actually reverse these a little bit if you want to. So you can switch these two. But let's just do it in the order they said first. Solve this equation for x in terms of y. If we want to solve for x, what do we have to do? So x is going to be? Then it says to express f inverse as a function of x, interchange x and y. What do I mean by interchange? So what does y equal? That is f inverse of x. When you plug in the outputs, you will get back the inputs. So let's go back and try it up here. X equals 2y minus 3. You can switch first if you want. X plus 3 is equal to? So what does y equal? Does that match what we got? Absolutely. What about, let's do a different one. Y equals x cubed. If we want to find the inverse, we need to switch and isolate. So let's switch first. So x is equal to y cubed. What are we trying to isolate? Y. What do you have to do to both sides to isolate y? Cube root. So y is equal to the cube root of x. Excellent. Okay, so let's take a look at the graphs. Let's see what these look like visually. Another pair is here and there. We graph this one. There's x cubed and y equals x. Just so you can see the curve a little better, let me change the window. Oh, and what did I not turn off? I didn't turn off the other two functions here. Let's make it negative 1.5 to 1.5, negative 1.5 to 1.5, and let's turn off those two. I missed it. I see what I did. So there's y equals the cube, x cubed, and here's the cube root. Now the question I want to ask you is, what do these relationships have in common? And I cut that off too soon. This goes like this, right? What do they have in common? So this right here is y equals x cubed, and this is y equals the cube root of x. They both cross both axes, that's correct. What we're trying to get at is, if I gave you the graph of one, Jonathan, stand up. Stand up. It's okay. If I gave you the graph of one, how do you go about graphing the other? Take a look at these two relationships here. They both intersect, right? Question is, where do they intersect? Meaning, see that point right there? Let's focus on that point. There's an origin here and here. What do you notice about those points? They're on a line. What line? y equals to x. If you have a function that takes the value 3 and maps it to 3, what does its inverse do at 3? Yeah. If 3 goes to 3 with f, what does f inverse do? Brings 3 back to 3. So if 3, 3 is on the graph, what has to be on the inverse? 3, 3. So what points don't move? What points are not being moved? The points where y equals x. Exactly. Let's graph that one more time and just see if it actually matches. You might have noticed I had it down there at the bottom. Take a look at that. There's y equals x. So the real question is, what does that help us do? What does that help us do? We now know it goes through the line y equals x, but what does that help us with? Well, let's say I didn't give you the equation for one of these functions, and I said make a graph. Let's look at one point in particular. Let's say we looked at that point right there. Let's call it a comma b. That's on the original function, y equals x cubed. If a comma b is on the original function, what other point has to be on the inverse? What point has to be on the inverse? If ab is on the function, what point has to be on its inverse? B comma a, exactly. So if AB is there, you know you go over A and you go up B. What else has to be there? You go over B and up A. What does that mean visually? And this is where I'm going to pull in a drawing, just so it's a little bit cleaner than my handwriting. Let's say you want to graph y equals x cubed plus 2. That's the cube of x just raised up 2. We just looked at y equals x cubed. So there's x cubed plus 2 right there. If you want to graph it, let's take a look over on the left. Let's look at this right here. This is important. You see that first AB point right here? What triangle is that on top of? What kind of triangle is this? It's a right triangle. If you switch that and make it that is the A value and that's the B value, you have an identical congruent triangles, but this is also a right triangle. Using basic geometry, you can prove that the distance from here to here is the same as the distance from that first point to there. This angle is a right angle, and so is this angle. So what do you call that? What have we done with the point AB? We have, it begins with an R. We've reflected over what? Not an axis, we've reflected over y equals x. So if you reflect a graph over y equals x, what do you end up with? The inverse. Exactly, right. Okay. What was our test to see if a function was one-to-one? Yeah. If you have a horizontal line, you use those horizontal lines to test to see if it's one-to-one. So there's y equals some constant c. Well, let's say you have the line y equals x. If I reflected y equals c over the line y equals x, what line does it become? If I reflect, it's a vertical line now. If you reflect this, it becomes a vertical line. What's the equation of that line? X equals what? X equals c. Because what does this point have to be? CC. So what do horizontal lines become when you reflect them over the line y equals x? So horizontal becomes vertical. So you'll notice in this definition, this is really important, in this definition right here, it says, let f be a one-to-one function with domain a and b. It's inverse. Remember, look how it starts with one-to-one. Why do we need one-to-one functions? Because if a function isn't one-to-one, what's its inverse going to be? Or I'll be more specific, what's its inverse not going to be? If a function doesn't pass the horizontal line test, what does that mean when you turn all those horizontal lines vertically? It's not going to pass the... And if a relation doesn't pass the vertical line test, it is not a function. So when you're running the horizontal line test on a function, what are you really testing? You're running the vertical line test on the inverse. So let's write that down. Is that kind of crazy? Running the horizontal line test on a function is the same thing as running the vertical line test on the inverse. Because all horizontal become vertical lines when reflected over the line y equals x. I'll make this bigger so you can see it. So you're doing all this reflecting, and what are you actually doing? You're just doing some tests, but not directly. We like functions, so we want the inverses to pass the horizontal and the vertical line test. If f is the inverse of g, if f is the inverse of g, g has to be the inverse of f. If f is the inverse of g, g has to be the inverse of f. Does that kind of make sense? A little cyclical there. What we now know is this. If you started with a value of s, f of s is going to be r. F inverse of r is going to be s. So what happens if I did this? What happens if I did f inverse of f of s? What's that equal? So what does it equal? Yeah. What's this? What about f of, well, let's leave it like that for now, okay? That should make, let's just keep it this one limited scope. The inverse undoes the function, so if you run the function and then you run its inverse, where do you end up? Where you started. Where you started. There's a nice little diagram right here. It's a pretty nice one right here. If you plug in x into f, you get f of x. But if you plug f of x into f inverse, what do you end up with? X. You end up back at the beginning. Absolutely. It's kind of cool, huh? So let's do a couple more. The graph of f inverse is obtained by reflecting the graph of f about the line y equals x. If you're ever totally stuck, you can literally fold your paper over y equals x, and you'll see an outline of what you want to graph. So sometimes you take a lot of pencil lead. You ever done a tracing like that? You do your pencil lead a couple times over, and then you fold it and kind of pat it down, and what do you end up with? A really light outline of the inverse. Sketch the graph of y f of x equals -1, the square root of -1 minus x, and its inverse function using the same coordinate axis. So without using your calculator, what? Pick, easy numbers, right? Good numbers, or ones that actually, you plugged in numbers that actually seem to work nicely. So how about the number -1? What do you get out? 0. You want to get what's the square root of 4? So you want to plug in what? Negative what? -5. So you plug in -5 and you get -1 minus -5 is 4, so you get 2. Then when you get the square root of 9, so you plug in what? Negative what? -10, and you get 3. So what is this thing going to look like? At 0, what is it? Sorry, at -1 it is 0, and at -5 it's going to be 2, and at -10 it's going to be. So what does this thing look like? Looks like that. How could we verify that? Well, you could graph it. Let's take a look. Let's turn all these off first. I'll keep y equals x on. So what was it? It was the square root of what? It's x, right? Let's do zoom. We'll do zoom standard. So there's y equals x. Hey, does that match? Absolutely. So how would you go about graphing the inverse? You reflect it over y equals x.
Well, I did that thing where you switch them and then.
You found the actual equation? So let's find the actual equation. So you switch them and use your hand motions. I like that. It's good. X equals -1 minus y, right? So what do you have to do to both sides? 1 minus y. So y is going to be equal to -1 minus what? So if we graph that, there's a slight problem, I'd imagine. If we graph this down here, -1 what? Minus what? X squared. If we graph that, it's too much, right? Let's go back and think about what we had before. Our original function up here, someone muttered it, I think it was you, John, it's very good. The original function, which I'll highlight right here, our original function. Here it is, right? What's the domain of this function right here? Less than or equal to what? -1. So what does the range of this one, what does the range of this one have to be? No, it's y less than or equal to -1, right? We need to do the range of this one, though. What's the range of this one? Y greater than or equal to? So what's the domain of this one have to be? X greater than or equal to? 0. So what do you have to eliminate here? The negative part. So what's the inverse here? The what thing? Oh, no, absolutely. No, totally. It still does. I'm just saying, I asked you to do it without doing this, but I'm saying if you did it algebraically, you might have ended up with this quadratic facing down. And how does that mesh? It meshes because you need to be cognizant, you have to be conscious of the domain and range restrictions. So if you're going to write this, you would say this specifically. F of x is equal to the square root of -x minus what? X? F inverse of x is equal to what? -1 minus x squared, right? But x has to be greater than or equal to 0. You have to state that domain. If you don't put that domain restriction in, is it correct? No, because is this right here in its entirety? Do you flip that over? Can you get that same function? No, you get too much of it. If you wanted to get this part right here, what's the equation for that one? It's the reflection over the x-axis, so what would it be? Negative square root of -x minus 1. Yeah, if you wanted it to face backwards and go down. Which you can do, it's fine. You feeling okay about this? Feeling decent?